Okay, we are going to begin Unit 2 on algebraic vectors, taking a look at vectors in two space. So really we're just taking any vector u and basically putting it on the Cartesian plane. Okay, so I've taken this vector u and I've moved it so that its tail is at the origin and its head is at some point P, A, comma, B. Okay, and the idea I want you to understand here, of course, then, is that this would be A, and this would be B. So I hope you could see then that we've created a right angle triangle, so we can see that the magnitude of u would be equal to the square root of a squared plus b squared. So just using Pythagorean theorem there to figure out the magnitude. And if we wanted to find the direction of u, we could use tan theta equals b over a. And therefore, then you could tell me that theta would equal tan negative 1 of b over a. Okay, and we write the ordered pair or the vector as square brackets a comma b. Okay, so the square brackets tell you that we're talking about a vector in the Cartesian plane as opposed to a point. And we can write this vector in a number of ways then. We can say that vector u obviously equals vector OP, as you can see from the diagram. So you're used to that. That is called the directed line segment. And now we can also say that that would be vector A, comma, B. So this is what we call a Cartesian vector or an algebraic vector. And OP is what we were using in Unit 1. This is a directed line segment or a geometric vector. So for your definition, we call u, vector u, which is a comma b, a Cartesian or algebraic vector, as I said, where the values of a and b are the x components and the y component, right? So this is like your horizontal and vertical components. So let's take a look at one and how we relate that to what we have been doing. Okay, so first thing I'm going to do is I'm going to draw this vector, negative 4, negative 5. Okay, so vector u is the vector that goes from the origin to that point P. Sorry, I don't have the ability in here to make those nice straight lines with my iPad, but that would be vector u, and I hope you can see that. Okay, and of course this length here is negative 4, and this is negative 5. Okay, so that is our Cartesian vector or our algebraic vector, and we're going to take that and we're going to make it a geometric vector. So let's start with the magnitude. Hopefully you can see that the magnitude of that vector would be the square root of negative 4 squared plus negative 5 squared, and that would give us the square root of 41. Okay, we're just going to leave that exact. And I'm going to find the direction of that vector, so I'm going to find this angle theta in here. Okay, and we can say that tan theta would be negative 5 over negative 4. Go ahead, pause the video, punch that in, and I hope you agree with me that that's 51 degrees. Okay, so reporting this geometric vector, say that the geometric vector u has magnitude root 41, and the direction, true bearing or quadrant bearing, your choice. I'm going to go with south 39 degrees west. Okay, so I hope that makes sense. Now I want to see if you can go the other way. So pause the video and see if you can take this geometric vector now and write that as a Cartesian vector or algebraic vector. So pause the video, try that yourself. Okay, so essentially this is similar to us finding the horizontal and vertical components, and I hope you can then see that the algebraic vector or the Cartesian vector u would be -3, 7 in square brackets. Square brackets are key to letting us know that it is a vector. Okay, so in general, then you might be able to see that vector AB is the x component, or if you like, the horizontal component is the magnitude of u cos theta, and the y component, or the vertical component, is magnitude of u sine theta, okay? And theta is the angle u makes with the x-axis, so very, very important that we're always drawing our triangle with the horizontal, with the x-axis. Okay, so we've seen this definition before, but hopefully maybe you remember we learned that a unit vector is a vector that has magnitude equal to 1. So there are two vectors into space that are significant here, and that's vector I and vector j. So I just want to draw those quickly to make sure that you can see those. So let's set that up. Okay, so vector I would be the vector that starts at the origin and goes to the point 1, 0. Okay, so that would be unit vector I. And then unit vector j would be the point that starts at 0, 0 and goes to the point 0, 1. So that right there. Okay, so picture what 3i would look like. I hope it makes sense to you that 3i would be that. And I hope it makes sense to you that negative 2.5j would be that. Okay, so going back to our earlier example of vector u, or vector AB, reminding you that this point is AB. Of course, you can see that in this triangle where that's A and that's B. Now, if I'm thinking about the unit vectors on here, just imagining what I drew above, that's unit vector I, that's unit vector j, and I hope then you can see that this section would be A times unit vector I, and this section would be B times the unit vector j. Okay, so just basically what we sort of drew in the picture. A times unit vector I is a vector that points in the direction of the positive x-axis, and it has the magnitude of whatever A is, the absolute value, right? It is positive, but it is magnitude, so it would always be positive. So we can say that the magnitude of A unit vector I would equal magnitude of A times the magnitude of unit vector I. We know that the magnitude of a unit vector is 1. And so really, that's why we say that the magnitude is just A. Okay, and of course the same is true for the vector B times unit vector J. So using our rules for adding vectors, I hope then that you can now see that we can say that vector U equals the sum of A times unit vector I plus B times unit vector j. Okay, basically we have our x component and our y component. Okay, so the next thing we're going to do is just make sure we're comfortable then with switching between the two notations. So we have two notations when we're referring to our algebraic vectors. We have the Cartesian coordinate notation, which is what we've used so far, and now there's also unit vector notation. Okay, so the idea here is just that if we have a Cartesian vector, -7, 8, we can also write that as -7i plus 8j. Go ahead, pause the video, make sure you can do the rest of the table. Okay, so a little bit of practice today, just understanding how to write Cartesian vectors. Okay, and the last thing we need to do is take a look at, well, what happens when the vector is drawn anywhere in the Cartesian plane? How do we figure out what that vector is as an algebraic or Cartesian vector? So suppose I have this vector AB, and let's just say that A is like 2, 3, and B is something like 7, 7. So this is a vector anywhere into space. Okay, we can basically take that vector and we can move it so that its tail is at the origin and it goes to some point P. Okay, so I'm going to take that vector, ignore that dotted line there, it wasn't drawn very well. So I'm going to take that vector and I'm going to move it to be right there. And we'll still call that P, and then you can see that it's at the origin. Okay, and I'm going to give you a minute to think about it, pause that video, and see if you could figure out what are the coordinates of P. In other words, what is this horizontal component and what is this vertical component. So hopefully you can see that this becomes 5, and this is 4, and therefore that point is 5, 4. Okay, and then we can say that vector AB is equivalent, same vector, same magnitude, same direction, to the vector 5, 4 in square brackets. And in general, if we have 2 points, A and B, then I can hopefully you can see that you got that by taking B1 minus A1, comma, B2 minus A2. Okay, and essentially this is the run, the horizontal component. This is the rise if we're taking a look at, let's say, the slope. Okay, so let's go ahead and try that in example 4. Do your best, see if you can pause the video and try that by yourself. You're going to express AB as a Cartesian vector through those points and also determine its magnitude. Okay, so to find vector AB, I'm going to take B1, which is 1, minus A1, which is negative 4, and then I'm going to do B2 minus A2. Okay, no work necessary there. I'm just showing it to you to make sure that you can see where that came from, but you should get 5, negative 5. And then if I ask you to determine the magnitude of AB, remember that it's just the square root of 5 squared plus negative 5 squared, and hopefully you can see that that is root 50. Good little reminder for you that root 50 can be written as 5 root 2, whatever the units are. Okay, good little reminder of your radicals there. So you're going to go ahead and practice this. The questions are listed below and in the outline.